Hello, everybody. Welcome to the recorded version of the endocrine system chapter. This is chapter 18. You have seen a few slides in this chapter, introduction to the hormones, the concept of receptors. There's a ton more to say. In addition to the lab material, we are going to dwell more on the physiology, some molecular action of how hormones deliver their message. But by and large, this will be a list of endocrine glands and their hormones and what they do for us. Maybe the biggest difference from the lab is the emphasis on the hypothalamus at the very beginning, and a number of these negative feedback schemes that your textbook writers use to illustrate maintenance of homeostasis by the hormones of these endocrine glands. So buckle up for the ride. A great chapter. Without endocrine glands and their hormones, we would be very, very different. And indeed, we may not be even around. If you think about the role of oxytocin in vaginal delivery. So definitely we're spending a little time with the endocrine glands. So let me start this screen share of the slides, and I'm going to make this eventually full screen. Right here. Okay, so this is a good starting point from the introductory aspect of this chapter, because this illustrates the very sketchy appearance of endocrine cells within endocrine glands as they are pouring their hormones into the bloodstream, and receptors are detecting those hormones, physically grabbing them and passing the message onto the inside of the cell. So we will examine in detail just what is happening inside the cell. How can a cell understand the instruction of the hormone? And as you'll see in a few minutes, this kind of scheme where the receptors are on the cell membrane is just one of the two ways how the message of hormones can be delivered to cells. We'll be seeing many examples of how hormones instruct the cells to create new molecules, how to change permeability of membrane. This just means that allows the movement of ions, sometimes water, through the cell membrane, and how to change chemical reactions, increase the speed of chemical reactions in most cases. We already mentioned this in lab, that the presence of receptors make cells into target cells. The more receptor a cell has, the more sensitive it is to the action of a hormone, the signaling of the hormone. But this is a little known fact that cells can make more or make fewer receptors. So on the target cells, the cells can decide to remove a large number of the receptors. This is called downregulation. And in some cases, target cells can decide to increase the number of receptors. This is upregulation. Instead of going into the effect in hormone deficiency or surplus hormones, it's just good to illustrate that the number of receptors can change very dynamically inside a cell. Here we are starting a classification of hormones. This is consequential because lipid-soluble hormones can pass through the cell membrane and deliver the message, the instruction, right to the inside of the cell. So any steroid hormone is lipid soluble, and those T3 and T4 hormones from the thyroid gland are also lipid soluble. So this is how lipid soluble hormones deliver their message to the cell. You can see the hormone here as this green hexagon, and without any hindrance, the hormone zips inside the cell, zips through the nuclear membrane as well, right inside the nucleus, where, as you know, way back from chapter 3, DNA is stored in the form of chromosomes. So here's the receptor for this hormone, and the receptor and the hormone together can bind to the DNA and make it available for the production of messenger RNA. A messenger RNA will be translated into a new protein. So very frequent consequence of lipid-soluble hormones is the production of new proteins. And the new proteins can have myriads of activities. For example, think about an aldosterone increasing the sodium absorption by the cell. So this new protein will be a sodium transporter or a sodium channel. And the more of those new proteins this cell has, the more sodium it can absorb. Or in case of estrogen, estrogen regulates the growth, for example, of the uterine lining. So if this cell is in the lining of the uterus, estrogen creates new proteins that forces the cell to divide, make more cells, make this lining thicker. The specific aspects of lipid-soluble hormones and their effects will be coming mostly in this chapter, although estrogen and testosterone, their effects we'll be seeing mostly in the reproductive chapter. So this is how lipid-soluble hormones can deliver their message and lead to the production of new protein. The water-soluble hormones, most hormones that we discussed in the lab and will be coming in chapter are water-soluble. These are proteins such as hormones of the pituitary. You see oxytocin here pictured. Look at all the amino acid making up this small protein. Epinephrine, norepinephrine, melatonin, calcitonin, parathyroid hormone. These are all water-soluble hormones, and they have a big problem when they want to deliver their message. Here is a water-soluble hormone in the bloodstream. When this water-soluble hormone wants to rush inside the cell, it's going to bounce back from a cell membrane like a tennis ball. Water-soluble hormones cannot penetrate into the cell because the lipid bilayer is a water hater, a hydrophobic layer, and it cannot allow and doesn't allow large water lover or water-soluble molecules. So what is this water-soluble hormone to do? The water-soluble hormone will find a receptor that is swimming in the cell membrane, accessible to this hormone from the outside. And a chain of events, a stack or a line of dominoes will be pushed over here. Once the hormone binds to the receptor, a G protein will be activated. The G protein will turn on this factory called adenylate cyclase. This factory will be making this product called cyclic AMP or CAMP. This cyclic AMP will be the major carrier of the message on the inside of the cell. So cyclic AMP is called the second messenger. Hormone is always the first messenger. Cyclic AMP for the water-soluble hormones is the second messenger. So what is the cyclic AMP going to do to change the mind of the cell? Cyclic AMP will activate protein kinases. These are enzymes that will add a phosphor group to a protein. And this phosphor group can activate or slow down the activity of this original protein. And so through this activity of adding phosphor to a protein, the effect of the water-soluble hormone will be felt. So think about antidiuretic hormone. When that antidiuretic hormone delivers its message inside the cell, the phosphorylated protein will be aquaporin molecules, aquaporin protein, and the phosphorylated protein can go into the cell membrane and form water channels. Those water channels will allow the cell to allow water to move through it. And so water reabsorption is possible by just changing the chemical nature of that protein aquaporin. The second messenger is typically cyclic AMP. Look at the list of hormones that use cyclic AMP as the second messenger. Sometimes calcium ions or cyclic GMP can also be used. And we'll see one inhibiting hormone. They will be decreasing the level of cyclic AMP. This inhibiting hormone will be coming from hypothalamus. We'll have a wonderful segment about the hypothalamus. So another advantage of second messengers is that they amplify the effect of water-soluble hormones. I'm going to go back a slide here. So a single hormone can lead to the production of thousands of cyclic AMP molecules. So out of one signal, 1,000-strong signal will be created inside the cell. That is where the amplification comes in. So when you look at these cells having all these chemical changes inside as a consequence of protein, it's important to keep in mind that all those changes are automatic. They are programmed into the cell. And just to illustrate how mindless these cells are in our body, here's the example of cholera toxin and G proteins. So in our intestinal epithelium, there are cells that are programmed to create intestinal juice as a consequence of a local hormone action. That hormone acts through a G protein activated pathway like we've seen before. In the case of cholera infection in the body, a toxin, which is a metabolic waste product usually of the bacterium, a toxin is going to interact with the G protein in the intestinal epithelium and lock it into the activated state. So the cholera toxin will mimic this intestinal hormone. So the intestinal epithelium will keep making intestinal juice. This overactivation will lead to a lot of liquid accumulation inside the small intestine. And the small intestine will pass this on to the large intestine, creating a watery stool. So this is where the diarrhea consequence of cholera infection comes from. And the cells of the intestinal epithelium didn't realize that they were tricked. They keep taking water and electrolytes out of the body, making more intestinal juice. So this is the mindless nature of the cell. Whatever activates this process, whatever pushes over this first domino, activation of G protein, the rest of the dominoes will fall in the cell and the cell will change its behavior. So for the cholera-infected person, this person needs electrolyte replacement and antibiotic treatment. Otherwise, the person dies in a matter of few days. And the person will die of dehydration because of the huge loss of water. Hormone secretion is under several layers of control. Sometime we will look at a number of negative feedback controls. There is one positive feedback, actually two in human biology that we'll emphasize, and both of the positive feedback controls are coming from the reproductive system. Disorders of hormone secretion can include either overproduction, hypersecretion. This was the cause of Robert Wadlow's incredible tall stature, too much growth hormone. But it can include also hyposecretion or too low level of secretion. And hyposecretion is the reason for type 1 diabetes. Insulin is secreted in very low levels or no insulin is made. In the sequence of endocrine glands, in the lab, we started with the pituitary gland. Here, we're going to illustrate the controlling role of hypothalamus. So we will be saying quite a few things about the endocrine role of this part of our nervous system, the hypothalamus. So the pituitary gland itself is made up of two lobes, the anterior and the posterior lobe. The anterior pituitary, where the hormones are actually made, are under direct control of the hypothalamus, which is located way up here. We mentioned this in lab. The posterior lobe or posterior portion of the pituitary gland is not making hormones. Hormones are just released here. More details are coming about that a little later. So how can the hypothalamus directly control the anterior pituitary? This is happening through hormones released from the hypothalamus. These controlling hormones will enter the blood circulation and then directly brought to the anterior pituitary. There is a very unique anatomical set of structure here. These are called the hypophyseal portal veins, these two blue vessels. These vessels allow the flow of hormone-rich blood directly from the hypothalamus. The anatomical curiosity of this is that venous blood is extremely rarely coming into an organ. Venous blood in general is drained away from organs. Here it's entering the anterior pituitary. We will be seeing one additional world famous example of a portal system, venous blood coming into an organ, when we'll be talking about the liver in the digestive system. Nonetheless, this anatomical curiosity allows the hypothalamus to make controlling hormones and immediately deliver them to the anterior pituitary for a quick response. So the first hormone that we'll be talking about from the anterior pituitary is human growth hormone. We abbreviated in the lab as GH. So while it does cause the growth of many structures in the body, here we're going to mention specifically this local hormone, insulin-like growth factor. Insulin-like growth factor is a middleman in this process. So when growth hormone comes, let's say, onto a cartilage, the chondrocytes first will make insulin-like growth factor And that insulin-like growth factor will stimulate neighboring chondrocytes to make more cartilage. So it is the insulin-like growth factor, IGFs, that are actually having the direct stimulation on the tissues. Growth hormone acts indirectly because we have this middleman, insulin-like growth factor. So this is a really good illustration of how hypothalamus keeps control of the anterior pituitary. So let's take a look at human growth hormone regulation in the blood. Blood sugar, blood glucose, but sometimes amino acids, fat levels, fatty acid levels in the blood. You can see it here and here are all regulating human growth hormone levels. So let's take a look at this negative feedback regulation. So hypoglycemia, too low blood sugar or low nutrient level is going to be monitored by the hypothalamus. The hypothalamus in response will release this GHRH hormone. This is a growth hormone releasing hormone. This purple arrow points to the anterior pituitary, and the anterior pituitary complies with the release the hormone instruction, and growth hormone will be released. Once growth hormone is in the body, the insulin-like growth factors will be acting on the tissues. This is the line way down here. And insulin-like growth factor will also be telling the hypothalamus that I've done my job. You can stop stimulating the anterior pituitary. In a case of too much blood glucose or too high fatty acid or amino acid levels, the hypothalamus will measure these conditions in the blood, and hypothalamus will release an inhibitory hormone. This is a GHIH, growth hormone, inhibitory hormone, and this blue arrow delivered to the anterior pituitary will stop growth hormone secretion. So this is how the hypothalamus, by measuring conditions in the blood, can adjust the working of the anterior pituitary as far as growth hormone production goes. In addition to regulating growth hormone release from the anterior pituitary, let's take a look at the list of other hormones of the anterior pituitary and what aspect of hypothalamus, what hormone from hypothalamus is regulating this. So ACTH is a hormone from the anterior pituitary, stimulates the adrenal cortex. The anterior pituitary receives permission from the hypothalamus through the CRH, corticotropin releasing hormone. Prolactin, which targets mammary glands to stimulate milk secretion. Anterior pituitary receives permission to make prolactin by the way of prolactin releasing hormone from the hypothalamus. So the hypothalamus controls ACTH and prolactin release from the anterior pituitary through these releasing hormones. Let's go this way. Here's more examples. Thyroid stimulating hormone from the anterior pituitary is released when the anterior pituitary is stimulated by TRH, thyroid hormone releasing hormone. Follicle stimulating hormone and luteinizing hormones, which have effect on male and female reproductive system, whether it's follicle development in the ovary, sperm development in the testes. the anterior pituitary needs to receive GnRH from the hypothalamus before it can release follicle-stimulating hormone or luteinizing hormone. And the effect of luteinizing hormone is ovulation in the ovary or testosterone production in the testes in males. And here's a hormone that we didn't, we kind of skipped this over in the lab, melanocyte stimulating hormone. So this increases skin coloration, but even this hormone, MSH, receives permission from a hypothalamus by the virtue of CRH. So the anterior pituitary is bound by the decisions made from the hypothalamus, and the hypothalamus is sending its instruction through these releasing or inhibitory hormones to the anterior pituitary. When it comes to the posterior pituitary, in the lab we mentioned the pipelines from the hypothalamus neurons all the way to the release point, the posterior pituitary. And this is the arrangement why we can say that the posterior pituitary is not making any hormones, it just releases them. So this is the end of the pipeline, and the hormones, antidiuretic hormone and oxytocin, are released at the ends of the pipeline while they were made in the hypothalamus. Just briefly, oxytocin stimulates uterine smooth muscles. This is the most consequential action of oxytocin during labor and vaginal delivery. This is subject to positive feedback. And antidiuretic hormone is responsible for absorbing water from urine into blood, and that decreases urine production, urine volume, and this is why it's called antidiuretic hormone. Antidiuretic hormone, we'll talk about this a lot in the urinary chapter. The saltiness or osmolarity of the blood is a major factor that controls antidiuretic hormone release. So with those lists of the pituitary, let's take a look at some pituitary gland disorders. So hyposecretion leads to pituitary dwarfism, very proportional body, but the size of a child. These individuals grow very little after birth. There's no physiological or mental issues with this kind of dwarfism. It's just a lack of stimulating hormone for growth. Hypersecretion, giantism, this is the disorder that afflicted Robert Wadlow, very tall, normal proportions. Robert Wadlow didn't live long enough to suffer from acromegaly. In somebody's 30s, 40s, and 50s, if this hypersecretion continues, there is disproportionate growth of hands and feet and some facial features. The thyroid gland is our next topic. And of course, if I'm going along, if you have any questions, please send me a message. I'm hoping that many of these terms, and of course the hormones, sound very familiar from the lab. Thyroid gland, I hope this is again familiar location. In the lab we had two models where we pointed out the closeness of thyroid gland to the thyroid cartilage, the Adam's apple. The thyroid gland has many follicles, the liquid-filled compartments. You see the artistic rendition of one of that, And the follicular cells making up the wall of this follicle, together with the colloid, the filling in the middle, are responsible for forming the hormones T3, T4, T3 is sometimes called thyroxine. So this is the sketch of how these hormones are actually made. Because these are unique hormones by the virtue of them containing iodine. The follicular cell, this hugely magnified cell, is taking up specifically iodine from the blood and pumping it into the colloid. The follicular cell also creates a thyroglobulin, TGB protein, and inside the colloid, iodine is chemically attached to the thyroglobulin, creating this very different iodine-containing molecule. This molecule is taken up by the cells, follicular cells, chopped up into small pieces, and those small pieces will be T3 and T4, depending on whether they had 3 iodine or 4 iodine attached to this small snippet of protein. And then, of course, secretion into the blood happens. Follicular cells are part of an endocrine gland, so the secretion will go into the bloodstream. So the function of T3 and T4, or thyroxine, is to increase metabolic rate. This comes with increased protein synthesis, degradation of fats to make energy for ATP production, and also increased heat production. Here's the artistic rendition of the follicle and the follicular cells. So they are responsible for making T3 and T4. And then on this artistic rendition, if you look close, there are clusters of cells outside of the follicle. These are the parafollicular cells. They make a very different hormone, calcitonin, and this hormone lowers blood calcium and moves the surplus calcium from blood into bone. We have seen a microscope slide of this arrangement in a lab, a little better than the artistic rendition that you see here. So how does the thyroid gland decide just how much T3 and T4 to make? Yet again, you see the role of the hypothalamus. Now, the hypothalamus have done a lot of things in our review already. In chapter 15, the hypothalamus changes our behavior from rest and digest to fight or flight response. You've seen in chapter 16, sleep, wakefulness, controlled by the hypothalamus. And now you are seeing hypothalamus controlling other endocrine glands, like releasing hormones like we'll be seeing here in a minute. And you have experienced that already with the example of growth hormone, but it is true for here that the hypothalamus can measure chemical components inside our blood. So there's a little analytical lab run in the hypothalamus. And so this analytical lab, among many other things, measuring how much T3 and T4 is swimming around in our blood. If as this scenario indicates here, step number 1, if the thyroid hormone level is too low, the hypothalamus will secrete TRH, tyrosine hormone releasing hormone. That instruction will go to the anterior pituitary, which will make tyrosine stimulating hormone, TSH, and that hormone will be going to the follicular cells, forcing them to make more T3 and T4. So this is how the hypothalamus becomes a very important monitoring station for how much thyroid hormones are made, T3 and T4, and the hypothalamus can take command through the TRH hormone, and the anterior pituitary takes it from there by making TSH to tell the thyroid gland, you need to create more T3 and T4. In terms of thyroid gland disorders, we have hypo and hypersecretion. Hyposecretion during infancy or even in utero will lead to a type of dwarfism called cretinism. Here, the features of this type of dwarf and dwarfism is not proportional, and there is some degree of mental retardation that is associated with this low level of T3 and T4 during infancy and fetal development. Hyposecretion in the adult has a very different consequence. Sensitivity to cold, low body temperature. Now think about this. If thyroid hormones increase heat production, increase the speed of chemical reaction, of course, when we don't have enough thyroid hormone, our core body temperature will drop and we will be sensitive to cold. Weight gain happens because the slow chemical reactions allow the accumulation of adipose tissue. Overproduction of thyroid hormone, hyperthyroidism, will lead to weight loss, tremors, nervousness, and there is an unusual consequence that adipose tissue will expand behind the eyeballs and push the eyeballs anteriorly. A good deal of the sclera is visible all around the, all under the eyelids, and this appearance is called Graves' disease. So this is a consequence of over-secretion, hyper-secretion of thyroid hormone. We also have a clinical condition called goiter, which is characterized by a hugely enlarged thyroid gland. So when there is too low iodine levels in the body as a consequence of low iodine consumption, the hypothalamus will measure low T3 and T4 levels and keep stimulating the thyroid gland to grow bigger and make more T3, T4. So in low iodine intake situation, the thyroid will be forced to expand. And so the thyroid will grow to the size of a walnut, to the size of a peach, to the size of an apple, and to the size of a cantaloupe. To avoid goiter development, in the United States, many food items, but especially table salt, is fortified by iodine. So if you go to a supermarket and you see a box of salt and that says red letters iodized, it means that it has artificially added iodine to prevent the formation of goiter in people who may not consume enough iodine in their daily diet. On the posterior aspect of the thyroid gland, and here you see the little snippet of thyroid gland in yellow, we do have yet another set of hormone-producing cells embedded there. They make a very different hormone, parathyroid hormone, and the producers called the parathyroid glands. The parathyroid hormone has effect on several body systems. The net effect is to increase blood calcium levels and decrease blood phosphate level. We'll take a look at a little detail of that in chapter 27, I believe, much later when we look at electrolyte regulation. We'll be mentioning that parathyroid hormone also regulates magnesium levels in blood. So again, a hormone or an endocrine gland is keeping an eye on chemical composition of the blood. So here is a set of negative feedback reactions. This is a combined illustrations of effect of calcitonin or parathyroid hormone. So let's take a look at this. Let's start with the scenario here. Too high level of calcium in blood. And this is a consequence of when you go on that 100% dairy diet and you consume cottage cheese, milk, cheese. What you consume contains a lot of calcium. Calcium absorbed through the small intestine will push up blood calcium levels. If anybody's taking high levels of calcium supplement in terms of pills, they will also have this kind of scenario. So to maintain a normal level homeostatic range of blood calcium, the parafollicular cells in the thyroid gland react to this, and they will secrete calcitonin. Calcitonin will slam the brakes on osteoclasts, and osteoclasts will stop bone degradation. Bone building will dominate in our bones, and the surplus calcium will be built into the bone and therefore decreasing blood calcium level back to normal. This is a negative feedback because we reversed the original challenge, high level of calcium. Now we decreased the blood calcium levels. Here's another negative feedback reaction. Our starting scenarios that we have too low level of calcium in the blood. We don't have enough. This happens a lot when we don't consume enough calcium in the diet. Calcium is slowly being released through the urine daily, so we can develop calcium deficiency. In that case, that condition will be detected by the parathyroid gland, and the cells in the parathyroid gland will create the parathyroid hormone. Parathyroid hormone will be telling osteoclast to degrade more bone. So calcium will be released from the bone. And the parathyroid hormone also slows the release of calcium into urine. Parathyroid hormone, as you see it here, number 5, stimulates the formation of calcitriol. This is vitamin D3. And vitamin D3 will tell the small intestine absorb more calcium. So to this three-pronged action, the parathyroid hormone achieves the rising of blood calcium levels. So we started from a low calcium level scenario, and again, through negative feedback, we reversed that challenge because we increased blood calcium level back to normal. When we look at the adrenal glands, we are looking at endocrine glands situated right next to on the superior aspect of the kidneys. I think we'll see this right here. Adrenal gland has a cortex and a medulla with very, very different hormones produced from both. Again, if you have seen the lab recording, then this will be very familiar to you. We have a model that shows this very nice separation of the cortex and the medulla. So from the cortex, one main hormone that is produced is aldosterone. This is a steroid, and it increases reabsorption of sodium into the blood. When we get to the mechanism that regulate blood pressure, this will be a way to increase blood pressure in a body. Aldosterone also promotes the release of potassium in the kidneys. So aldosterone increases blood sodium levels and it decreases blood potassium levels. Another hormone from the cortex is cortisol. This has two effects. The metabolic effect of cortisol is to instruct liver and skeletal muscles to release glucose into the bloodstream, and it is also convincing the liver to take amino acids and turn them into glucose. So glucose levels in the blood will be raised as a consequence of cortisol action. Cortisol also has an anti-inflammatory effect because it inhibits white blood cell action, and inflammation, as we'll see in chapter 22, is a consequence of white blood cell communication. Chemicals released by white blood cell cause that not only the blood vessel dilation, but also the triggering of pain receptors. So cortisol, or its medical form, cortisone, is used to find inflammation inside joints or topically on skin areas. The last hormone is DHEA from the cortex. This belongs to the group of hormones called androgens, or masculinizing hormones. Adult males have plenty of testosterone for masculinizing, so it's not important. But in females, this can be converted to estrogen, which is a major driver of breast and uterine cancer growth. And for normal biology, DHEA increases libido, sex drive in females. The adrenal medulla, totally different ball game. No steroids are made here. The hormones that are made here are epinephrine, norepinephrine, and norepinephrine is identical to the neurotransmitter from the sympathetic division of our nervous system. The adrenal medulla is under the control of the sympathetic division of nervous system. So nerve endings come to this medulla and stimulate the release of epinephrine and norepinephrine hormones. These hormones mimic the sympathetic action of our nervous system. Therefore, fight or flight response or fight or flight behavior is stimulated, increased heart rate, increased blood pressure, increased sweating, dilation of the pupil, and increase in the diameter of the bronchioles inside our lungs. Here we're going to start to talk about endocrine organs that have other jobs. So the pancreas is an organ involved mostly in producing digestive enzymes. In the digestive system, we'll detail its role. Here, we do have to mention that inside the pancreas, we have these pancreatic islets, and the alpha cells inside the pancreatic islets produce glucagon, beta cells produce insulin, and glucagon and insulin both regulate blood glucose levels, and we do have a negative feedback scheme, a regulation here. So let's start with the low blood glucose hypoglycemia. This is 2 in the morning, and our body is using glucose, but there's no new food coming into the body to replace it. So low blood glucose levels develop in the middle of our sleep. The alpha cells will detect this. They secrete glucagon, and glucagon goes to the liver and tells the liver cells to take glycogen, change it into glucose, or make glucose from other substances. This glucose from the liver is released into the blood, and so blood glucose will be normalized. Again, we took a low blood glucose scenario and reversed it. So this is negative feedback. We normalized blood glucose levels. When we start with hyperglycemia, high blood glucose levels, normal an hour or two after consuming a meal, it's the beta cells that react to this condition. They secrete insulin, and insulin acts on virtually all cells in the body and help these cells to absorb glucose from the bloodstream. The consequence of that, the blood glucose levels fall. And so yet again, we reverse the initial challenge, high blood glucose, into a normal blood glucose level through the decrease of blood glucose, consequence of action of insulin. We mentioned this in lab a little bit. Type 1 diabetes is an instance of a missing hormone. Insulin is not made. Type 2 diabetes is a disorder of receptors. Receptors are too few in numbers, and sometimes the receptors are misshapen. They cannot detect insulin in the blood. Very different origins. However, the pathology, the hyperglycemia, too high blood glucose level is the same for type 1 and type 2 diabetes. A few words about other part-time endocrine glands, ovaries and testes. We'll detail these in the reproductive system to a lot greater degree. Ovaries, estrogen, progesterone, most typical hormones that we will mention even later on, regulating the female reproductive cycle, maintain pregnancy, major roles for these, although estrogen has receptors in almost all cells in the body, so there are a lot more widespread action coming from estrogen. Testes, the hormone testosterone is a main steroid produced here, stimulate sperm production and help the forming of secondary male sexual characteristics. Testosterone also has receptors in almost every cell in the body, and we'll be seeing effect of that as we go through many, many chapters. I do want to say a few words about pineal gland. Now, this is an honest to goodness endocrine gland. There's no other role for it. This is close to the third ventricle of the brain, and melatonin is the hormone that's made here. Melatonin is a hormone that helps the hypothalamus to maintain the sleep wakefulness cycle. When the amount of sunshine is too low outdoors during the winter months, a depression might occur because of low melatonin level. And I'm sorry, I explained this wrong. So depression occurs because of the overproduction of melatonin. Melatonin is produced during nighttime, and it produces this subdued, sleepy nature to our body. And I believe the last example here of a part-time endocrine gland is the thymus. will be explained what in the world T cells are when we go to the immune system. These cells, the T cells, are major fighters, a type of white blood cell in our immune system. And the thymus gland is a site for the maturation of these T cells. To promote maturation of the T cells, there are internal hormones, thymosin, thymopoietin, are all stimulating this activity of the thymus gland. So this was the chapter 18 view of the endocrine system, a little more extensive than the lab, but by and large, we covered most of the identical endocrine glands and their hormones. So I'm going to stop sharing here. Let's see if I can do this. All right. So please let me know if you have any questions about this endocrine chapter, and I'll be attaching this to your class as soon as it's done uploading. So thank you for sticking with this topic, and have a great rest of the day, rest of the week, and I'll see you all on Tuesday. I'm going to stop recording here.